future is plastic. At least that's what everyone used to say, and they turn out to be right, and there doesn't seem to be any sign of that changing. So why are we so addicted to plastics? Why are they so brilliant? And why are we so scared of them? You know, are they really that damaging? Is there a future where we could be not worrying about plastics anymore? So in this second episode of Sculpting Tomorrow, we're going to be getting right to the sharp and asking, is there a future without fear of plastics? Or are we just going to get rid of them? What we're going to do next? So this is our second episode of the podcast, and we want to get away from the media hype and get down to speak to the real people who are actually at the cutting edge, thinking about how we shape the future and what the choices are that we have to make as a society. So today I've got two researchers who are in from the Innovation Centre for Advanced Sustainable Technologies.
So close.
Circular.
Applied Sustainable Technologies.
See, that's good. What happens when I don't use my notes? Innovation Centre for Applied Sustainable Technologies, ICAST. Okay, and that's part of the University of Bath.
It's a joint between the University of Bath and the University of Oxford.
Okay, and so do you want to introduce yourselves and how you fit into that?
Yeah. So hi, I'm Dr. John Husband, and I'm a researcher at ICAST. My focus is mainly on improving the recyclability of plastics, whether that's improving the plastics themselves to be more recyclable, or also looking at technologies to recycle them much more efficiently to help stop the leakage of plastic into our environment, which we see.
Okay.
And I'm soon to be Dr. Philip Yang. I'm also a researcher at ICAST, and I specialise in making plastics from sources that aren't petrochemicals and fossil fuels and things like that, and trying to replace the current industry plastics that we have today with better plastics.
Okay, so but what we're clear about is Dr. John and not quite Dr.
Like one of the letters I can have, just not the full DR.
Just not the full DR.
No.
Okay. So that means you've just finished a PhD and you've vivaed and all that sort of stuff, and basically they're making you correct any mistakes in your thesis.
Yeah.
Of which there were not too many.
Quite a few typos, but not many.
Okay.
Not many otherwise. Yeah.
Yeah. So just really, I want to start from scratch, really. Well, firstly, about you guys, what brought you to here? I mean, clearly, I suspect you played with plastics when you were kids. But what got you into that field of research? What degrees did you do and why?
I'll let you go.
Yeah, so I was always into science, big, when I was a kid. I always wanted to be a scientist. And that's just how I decided that my kind of academic and educational path would be. And chose to do a degree in chemistry at the University of Bath.
Right.
Finished that, and still love chemistry. Nerdy, I know. So decided to do a PhD in chemistry.
You're allowed to love chemistry. That's the bit with the explosions.
Well, yes.
So
hopefully not, though, if you're doing it well. But so then, I saw an advert for a PhD in polymer chemistry at the University of Warwick, and I knew I was really interested in plastics and polymers, and I knew that there was the big industry and there was a good employment prospects with a PhD.
What got you into science? Was it just a brilliant teacher, or was it something outside school?
I don't know. There's something I always wanted to know about the world around me, and I was asking why.
Okay.
And in the end, the answer is science.
You must be
science is just studying why is this the way it is.
Yeah.
You were a really irritating kid, weren't you?
Yeah, absolutely was. My mum called me the why child.
Yeah.
Kid,
Yeah, the quiet child and the be quiet child. Yeah, yeah, fair enough. How about you, Philip?
So I did a chemistry degree as well at the University of Nottingham.
Okay.
And I was initially into pharmaceutical chemistry and drug discovery and things like that. But I did a.
Is that from Breaking Bad, or?
No, I wasn't old. I didn't watch it at that time. No.
Okay.
But I did a placement year at a company called Akzo Nobel, who make Dulux, the paint. Right. And for that year, I spent time trying to look at replacing some of the petrochemical derived plastics, or parts of the petrochemical derived plastics, with naturally derived materials.
Okay.
So I got quite an early exposure to those types of projects, and then continued that on in my PhD, where I looked at kind of more from the ground up, making new types of plastics, mostly from sugars.
So you finished a degree, then you went basically into the working world, and then came back to the PhD.
I did my working in the degree, so I did a degree called a Chemistry of the Year in Industry.
Okay.
So I did that.
Yeah, that makes sense. Okay, so getting into plastics, let's just start with, we hear all the big stats, that whole, is it by 2050 there'll be more plastic than fish in the ocean, which is terrifying. It doesn't sound good. I've been interviewed on the local radio station 105 by a kid called Ayan who presents a lot, and he was quite worried about microplastics. Is there microplastics in my food? And I was like, well, there's probably some in the air and the water you're drinking, to be honest. You probably full of microplastics yourself at this point.
Yeah.
So I don't know, was I scaremongering? Is that true? How worried should we be? How big of a problem is it?
I mean, in terms of microplastics, like there's not loads of, there's not really any evidence to suggest they're actually bad for you, but obviously it's not a good thing to have millions of microplastics in our oceans and in humans and things like that.
I think because they're so new, there's not a lot of science being able to show long-term effects.
Yeah, but the absence of evidence isn't evidence of absence,
Exactly.
is it?
Absolutely.
We weren't worried about asbestos for a long time, or all sorts of things, till we got the evidence that it was bad.
Exactly.
So I guess it's more precautionary in many ways, though.
Yes.
We don't know what this is going to do. It might be inert, it might be bad, but actually, let's not fill the environment with stuff.
Let's not disrupt marine environments. And
That's for sure happening, right? When you look at the Great Pacific Garbage Patch, that's definitely affecting the ecosystems in the ocean, and we know that all over the world. So
and I guess that's before we get into what we have to do to create the plastics. So really, basically, then, I mean, plastics are in everything. When we went through the pandemic, we were all throwing away daily plastic tests. There's a huge amounts of plastic. All medical supplies are plastic, toys are plastic, but food comes in plastic. We just can't do without plastic in modern society. It feels like we just have it in pretty much everything. So what is it? What is plastic, and why is it so good?
So at the moment, plastic is generally taken from oil from the ground.
Right.
It's refined. It might be distilled into to monomers that make plastic, and then it's polymerized. So basically, it is oil that's been specially treated in a chemical process to make hard, malleable plastic that makes the materials that we have around us. So we are taking carbon from the ground and bringing it out, polluting the atmosphere.
And monomers is like single unit polymers being several
exactly.
together.
So you have one monomer that repeats again and again and again and again. You get to a certain length, and it becomes a polymer.
And why is that useful, though? Why is plastic turn out to be?
Well, you can have so many different monomers, and you can make so many different plastics as a result. And minor changes chemically to those monomers gives you a massive difference in the material that you get out in the end. Whether it's really, really flexible, whether it can be used for more kind of mechanically kind of testing applications, or as a result, there are plastics basically everywhere, because you can have a plastic that's really good for paints and coatings. You can have a plastic that can go into your cosmetic products, your personal care products. You can have one that can be other materials to make toys or anything like that. So because of the variety in what you can start with, you have a massive variety in what you can make out of it, and because it's a synthetic material that's hundreds of building blocks stuck together, it's really, really tough and resilient and a bit of a wonder material.
Okay, so it's just the versatility then, isn't it?
Yeah, and the cost is so low, right? It comes as a side product from taking fuel out of the ground and gas, so there's an abundant resource there, and it's cheap.
Yeah. Okay. Which brings on to another part of the problem, I guess. So okay, that's kind of what it is, why it's so useful. It's basically just massively versatile. Yeah, wonder material. It is, and I think people worry about plastics on vegetables and stuff in supermarkets, and there's a kind of weird, when you do the maths, you're better off having the impact from the plastic often than not having it, because the amount of food waste you produce from a carbon footprint. So it all gets quite involved, doesn't it?
This is where plastic becomes a particularly powerful material, is actually its carbon footprint is very low. And because one of the main issues facing us as a society, I would argue today, is climate change, plastic might come in really, really handily for solving climate change, because, like you say, if you're preventing food waste, which is really carbon intensive, you're saving on carbon there. But also, if you think about other materials like metal and glass, because they're made at such higher temperatures, they take a lot more energy. And so metal, like 500 or 600 degrees to melt, glass over 1,000. The amount of energy that goes into that is so much more, and the carbon footprint of those is so much larger, that actually, from a global warming perspective, Plastic looks much better, 200 degrees, 150, something like that.
So when I said at the beginning, the future is plastic, it's slightly provocative because basically plastic, if you say plastic, people think evil, enemy, horrific. But you guys sound like you're big fans. Is that fair?
I think I don't like non-degradable plastics, so the ones that just stay around in our environment. We can phase them out for sure. And I don't like the fact that it comes from oil, which is, contributes to climate change and things like that. So there's things we need to change about plastic for sure. But in terms of its carbon footprint, in terms of what it can do for what it is, it's very, very good.
I think it's key to understand what's not massively been portrayed in the media is that there are good plastics and there are bad plastics. It just so happens that a lot of the plastics we use today are the bad plastics,
right? Okay.
or ones which are currently used in a way that isn't massively sustainable.
Yeah, okay. So it's like the whole good bacteria, bad bacteria thing will happen again.
Yes.
So okay, that gets on to you were saying about it's coming from oil and this whole bad plastic thing. So your work is often described as related to the circular economy. What does that mean?
The circular economy is a way of representing the supply chain of, let's say, in this case, plastics. So a linear supply chain comes from fossil-based sources, gets processed, made into goods or whatever, that gets used and then gets disposed of. There's no circularity in that. The disposal is usually going to be incineration or landfill. So the carbon you're talking about is coming from underground, being used and then sent into the atmosphere.
Right. Dig it up, use it, bin it.
Exactly. And that is not a sustainable process. The fuel's going to run out and we're going to have climate change because of the carbon in the atmosphere. So what the future needs to be is circular, where we don't start from fossil-based sources and we don't incinerate and landfill. We reuse and recycle. So it's about making plastic from sources that are renewable. So that we're talking there plant-based plastics, bio-based plastics, and then having systems to circulate that in the ecosystem all the time.
And that's like not really a new idea. I mean, in the sense of like nature does that constantly.
Yeah.
Things grow, they die, they turn into mulch, and it just never ending. So you reuse the same stuff.
Perfectly circular carbon economy, doesn't it, if you think about it?
And then we came in.
And then,
then we came in. Went, here's some oil. So get in more details what you actually do then. So you work more in that kind of oil. What to do about the current type of plastics from oil?
Yeah.
Is that
So
right?
I spent 2 years at a chemical recycling company here in Swindon, where we were looking at recycling some of these really tough plastics that are really hard to degrade. So the process that kind of typically involved in that kind of recycling, so it's 500 degrees, 600 degrees, and you're really heating up these polymers to the point where they just break apart. And then you collect all the things that are broken apart, you refine them again, and you turn them back into new plastic. So it's quite an energy intensive process, but it's very good at burning off things that can't be recycled. So if there's food contamination, other plastic contamination, other material, paper contamination, it'll burn off, and all you're left with is this recycled plastic that you can keep going. So that was what I got experience with. Now what I'm looking at iCast is, can we do that at much lower temperature? So basically what we're developing is a little molecule that can attach to your plastic and just unzip the chain. So like we're talking about those monomers, one by one, take off the monomers back by back at maybe something like 100 degrees. So much lower than the 500 or 600 that it's really challenging to make work in the economy, because 500 and 600 degrees is a lot of energy and a lot of cost associated with that, but also has a much lower carbon footprint. So that's my main focus, is can we unzip these polymers effectively at much lower temperatures.
And so it wouldn't take oil out of the situation. I mean, you wouldn't need new oil.
So the way I would see it is, yes, at the moment that is completely a fossil-based ecosystem, and we would be looking at just taking those fossil-based plastics and making sure they're not going into the environment, but we're reusing them and recycling them. However, you could envision the same technology working for bio-based plastics. It's just we need that technology to develop the bio-based plastics first. So at the moment, the whole supply chain is fossil, so therefore the recycling is going to be focused on fossil-based plastic.
Yeah.
But if we have a bio-based input, then we can use that instead. That's no problem.
And it feels like that'd be a kind of a pretty awesome situation if the waste plastic we have now suddenly had a value.
Yeah.
And there was people were incentivized, or companies were incentivized to clear up the oceans because actually you can reuse that plastic. Whereas at the moment it's kind of someone else's problem.
Yeah, I mean there's several charities that go around collecting it all.
Yeah.
But it shouldn't have to be charitable work. It should be, there should be a value. There's a lot of value and money in the carbon that's floating around in our oceans.
Yeah.
Yeah.
let's get out and
It's
use it.
just cheaper at the moment to use oil.
Okay. And where do you fit in? Actually, before we get to that, have you got any examples of that sort of thing, or is that?
In terms of
what sort of things get used, or what is better for? I mean, before we go into plants, are there things that are better used from the oil-based plastics, or is it kind of more or less the same?
Can you think of anything?
Anything that is better?
Better as a fossil base at the moment. I mean,
it might be no. Maybe we're not losing anything.
I don't know. I guess some plastics are so over-engineered to be what they are that, yes, currently they're better as fossil based. So Lego, for example, it's a very, very, very well. It's a very tough application actually, because what you want is a Lego brick that's never going to deform or creep over 50 years, 100 years, because you want that to click in place every time. And so, Lego themselves have tried with plant-based plastic before, but because these issues with creep and stuff like that,
you can't beat the
you can't beat the fossil at the moment. But that doesn't mean it won't get there 100%.
Right. But right now they have a real value and application. Yeah. And so where do you come in? What's your
So I mean, my role to John's is a little bit different at iCast actually as well, which I forgot to mention. In terms of what I do, we work on short-term projects with industrial companies as part of iCast. So a company will come to us with, say, a 6-month project to kind of get an idea of the feasibility of a certain sustainable technology. That could be like making something useful out of a waste product that they've got in their process, or it could be making a new plastic from a naturally derived material that they want to use. While John is also working on kind of the core research at iCast, we're also working with industrial companies to bridge the gap between what universities do, which is the straight research, and what what industry does, which is making products and making kind of commercial plastics that you see in your products today.
So take it from like just a theoretical thing to actually real problems.
Yeah.
So you're not just solving something and the world goes, actually, we didn't need that, but well done.
Yeah.
Very clever.
We're actually trying to replace current materials that are in use today that are derived from petrochemicals.
Okay, so have you got examples of that, or what you do and the sort of how the plant-based stuff works?
Yeah. So one of the projects that we have going on at the moment is making a bio-based plastic that is coming from mostly trying to take this thing called isocyanates out of polyurethanes, which are very popular plastic, and it's these isocyanates they're a type of monomer, and they're incredibly toxic, and there's a big push from industry to take them out of the plastics that we have today, and still retain the properties of those materials because they're incredibly useful.
Right.
So things like polyurethanes, they're used in all manner of random applications. So like something like a football boot, the outsole, the bottom bit that kind of connects to what you run on when you play football is a polyurethane.
Okay.
And trying to take out some of the most toxic or the most like unsustainable components of those is a big push of what we're doing at the moment, and making also kind of valuable products out of waste materials that companies are producing as part of their main processes.
So what have you brought with you?
So we've brought in essentially some materials that you can make plastics out of.
Okay, that aren't oil.
Which are completely natural materials that are maybe a bit mundane to you, but we can make some very nice materials from them. So I'll start off with I'll just bring them all out actually. You've got some table sugar, you've got starch, you've got something called cellulose, you've got standard vegetable oil that you may see in your kitchens, and I'll bring out some straw. It's
a bit murky that. I'm not sure I'd cook with that.
Yeah, maybe not.
So just for people who are listening, so what you've brought out is, if you imagine in school the little conical flask, so like an upturned triangle, but with caps on them.
Yes.
And they're kind of they're just kind of big enough to sort of fit nicely in your hand. That's good lobbing actually.
Yes.
They're like good Molotov cocktails out of those. That's the sort of size of them. Have you never done that? Wouldn't you?
No, I missed that
You've gone to protest. What are you doing? I thought you'd been students. Anyway, but inside them is a series of different kind of products. But 3 of them just look like flour, because it's just 3 kind of white ones, including the sugar, and then one that's full of straw, so it looks like the world's smallest rabbit hutch, and then the murky looking vegetable oil.
Yeah, it might not be of food grade anymore.
May no longer be food grade. So you're saying you can make plastics out of these? So tell me about those.
So yeah, I mean, I'll start with table sugar, which is the most common example. There are loads of different monomers, as we called them, that you can get from processing and fermenting sugars into different materials. So the most common plastic or bio-based plastic that you have today is called PLA, polylactic acid.
Okay.
And that comes from, if you ferment sugars, you can actually get something called lactic acid, which is the same thing you produce when you do too much exercise or when you run. And you can turn that into a plastic. Plastics that is used today in things like packaging applications, and even in artificial hips and knees. They're PLA because it's bio-based. It's quite biocompatible.
Right. Okay.
But
it's really no longer sugar. So it's not going to like melt and dissolve in your knee.
Exactly. It's a material that comes from sugar, but we're making a different chemical that we can turn into a really, really strong and useful plastic.
It won't melt, but because it's bio-based, it has bio-based linkages in its backbone, and so it will biodegrade over an arguably longer period of time than maybe we'd want, maybe 10 years, 20 years, 30 years.
You can compost it it will just...
You can compost it. So
which is handy if it's in a knee.
Yeah,
it is. Yes, but it is going to last for enough period for it to be used and then degrade away and not just pollute our environment.
Okay. And when it degrades, you end up with building blocks which are natural.
Well, lactic acid. Okay. It's going to degrade back to lactic acid.
We've got some PLA, haven't we, as well? Actually,
what's that?
There's PLA. Actually, this is another sugar-based plastic, isn't it?
Well, that one arguably is from cellulose.
Oh, okay. No, it's true.
Yeah.
Bit of both. We'll come back to that.
Okay, so this is, you take the sugar, you make the polylactic acid.
Yes, well remembered.
Awesome.
Amazing.
There you go. So these are just little granules. It looks like you've accidentally opened a beanbag or something.
Yeah, there's just pellets of
and
them.
tiny little
That's the easiest way they're made, right? You extrude the plastic and melt it to 200 degrees into like this kind of fine tube, and then it gets chopped up loads of the times into granules, and they can be shipped, remelted into.
It's just a kind of a useful way to have it delivered.
Flowable.
Yeah. I can have a scoop of this, however much of it I want.
Exactly.
Okay, and then so that'll go to a manufacturer who'll make a knee out of it, or joint, or whatever it is. When you say packaging, that's kind of
like plastic bags you can get from PLA.
Some of the most common types of degradable compostable bags will be PLA.
Food waste bags.
Food waste bags, yes.
Okay, that makes sense.
So if we think, we compare that to the fossil-based plastic, the only real reason we don't use that is it's probably something in the region of 20% more expensive than fossil-based plastic. So there's a little bit of a premium, but it's not a massive premium to be paid to have that.
Yeah.
And that's the only disadvantage currently, is the price.
Yeah, I mean...
Yeah.
And presumably that would change with scale. It's just the problem that oil's so cheap.
Yeah.
It's probably the...
Yes, and there's so much of it.
Whereas you have to manufacture that.
Yes, and companies have to invest a lot of money into building plants to deal with that rather than oil, right?
Okay,
so if you've got
it's like a retooling thing.
Yeah, if you've got $1 million plant that's processing oil, it's going to cost you a lot of money to retool that into something.
And also, if you've got kind of a starting material that comes straight from just oil, then that's just one step, and you've processed your oil, and then you've got the material that you can make a plastic out of. If there's additional steps in terms of turning these natural materials into fermentation and then further kind of chemical transformations to make something that can then make a plastic, like that in itself has a carbon footprint that has to be.
So I mean, the end point is a material that's 20% more expensive, but the big cost is the change in infrastructure between getting from A to B.
Yeah.
That's probably the big lump, isn't it? Which that means government flipping interventions, isn't it? Like, let's incentivize people to move. I don't know.
Yeah.
But okay, that's really interesting, because that feels like that's not far in the future. That feels doable tomorrow, or today, essentially. What else have you got?
So I'll continue with the curious white powders. We've got cellulose.
What I like to hear.
And we've got starch. So starch, the same thing you find in potatoes.
Right. Crisps that have been stored too long.
Sure,
Potatoes
yeah.
been stored too long.
And you can turn that into plastics. There's things called thermoplastic starch, and they can be used for different applications. You've also got something called cellulose, which is really useful, and it's being used by a company at the University of Bath to make microbeads for kind of cosmetic products.
So instead of non-degradable plastics, the beads that you'd get in exfoliants or whatever, you'd have a degradable cellulose bio-based.
Also,
so you can have sustainable vajazzling. Essentially, is what you're saying with this.
You can also, this is already in use today, and things like cling film come from cellulose. Can come from cellulose at least.
And that's completely impossible to recycle at the moment. Presumably, cling film.
It depends,
It
because
certainly doesn't go in my plastic recycling bag, does it?
No, I mean, if it's cellulose-based cling film, it should degrade.
Okay.
because it's so thin, it would just.
Yeah, it should compost fairly well,
Right.
especially at an industrial scale.
Okay. And so is there, the starch, that doesn't go to the same as this, because starch and sugar, in my head, they're both sugars. But is it completely different?
You can turn the starch into sugar, chemically.
But that's not what you do.
Well, no, the other option is you actually turn it into other types of polymers. So we do have an example.
If I can find the thing. Yes, we do.
At the end, I'm going to just test you with bits of. It's like my son.
Don't do that.
My son's colourblind, and so for a while we discovered everyone kept saying, "So what colour did you see this?" Really annoying him. Did you just go, what plastic is that?
That's the starch we were talking about.
Yeah, that's the thermoplastic
so
starch.
This is thermoplastic starch, which is.
So that looks like a little plastic sort of petri dish kind of thing, but again with a flat lid. And oh right, okay. So it just looks like you've. I was thinking this was just the packaging of the plastic, but it is the plastic.
Could just be packaging.
It looks like you've burst a white balloon and scrunched it up in there, or like plastic tissue paper. So yeah, this is thermoplastic made from starch. And what's the applications of that?
I think things like packaging again you can use for it's the thing with a lot of these naturally derived plastics is they aren't everywhere. So we're still looking at ways to kind of optimize the materials we can get out of these and see what they can still be used for at the moment. But things like packaging, I think that would definitely be used for as well. Yeah,
and I guess if a company's coming to you going, we want to make this change, you kind of go, well, here's your options.
Yeah. Mm-hmm.
But then you need to do the innovation and the research to kind of make it work for their particular application. So what else? What's with the straw? That feels unlikely.
It looks like a plastic already, doesn't it?
It kind of does, except if you're kind of putting in people's heads, natural and unnatural, man-made, you kind of put straw way down the natural end, and the plastic's kind of the other end. Does it feel like they should be connected?
Well, the best thing about this is that if you break it down, you can get cellulose,
right? Okay,
and you can get something called lignin as well, which is very commonly, it's another very useful kind of bio-based material that you can use for a variety of different applications. So it's called, you get lignocellulosic biomass, I believe, from it.
And if you separate the lignin and the cellulose, you get cellulose powder, which again can be turned into plastics, and then lignin, which is a valuable feedstock chemical.
Yeah.
So.
Okay. So finally, the vegetable oil.
Vegetable oil. So vegetable oil is a really useful and cheap source of sustainable plastics, namely because there are so many different types of oils, and there's a lot of oils that aren't used for kind of food sources, things like soybean oil and linseed oil, which can be turned into plastics. It's quite common to make something called epoxidized vegetable oils, and if you ever heard of the term like epoxy resin and things like that, like you can make these types of resins out of vegetable oils as well. So that one kind of looks.
Delving into your box of
It
goodies.
looks a little bit more how you might expect a naturally based plastic to look. It's a bit brown.
What, murky?
Yeah. and you can get kind of a resin, and you can imagine that as a kind of
sealant or
or adhesive or epoxy resin or anything like
so that would be supplied when you manufacture it. Is that supplied like beads, but you kind of melt it down and create it into whatever shape? Because this basically looks like a bit of broken stained glass.
Yeah, I mean, it
would be a liquid that would set on exposure to
heat or light or
light.
yeah.
Exactly.
Okay. All right. So and what was this? You say the application for that?
You could use it for things like adhesives or any kind of materials applications. You can also strengthen them by putting some kind of you can make what's called a composite, where you put some kind of strengthening material in with the resin as you make it.
So one of the common things would be like a carbon fiber composite, where the carbon fiber weave gets intercalated with all that oil, and then it all sets really, really hard, and you get a super strong interaction between the oil and the fiber, and you get a really strong carbon fiber.
So it's equivalent of a reinforced concrete. Where reinforced concrete, you have metal strips inside concrete, and they add strength to each other. So you're essentially doing the same thing,
Just
but
toughening it.
this is your concrete with the metal being the carbon fibre.
Yes, exactly. And that will form, some of the future technology for sure, like airplanes and stuff, will need lighter and lighter material to make them greener. And so if we can use bio-based versions of the lighter materials, that's even better.
Okay. So I mean, it feels like you've got, you're presenting like you've got it covered, essentially. Like you've done it, you've solved it, we've got all these different things. What's missing? What can't we do? And why are we not just using this?
Well, these materials in themselves can't cover every application of plastic at the moment. And a lot of the time...
Do you think it's like 5% of the applications? Is it? Where do you think we are?
I mean, currently, there are, say, in the last year or so, there was 350 million tons of plastic produced in a year.
Right.
And about 1.5 million of those were these types of plastics, like bio-based and naturally derived ones.
What sort of percentage is that?
Less than
1%.
Less than 1. And
so people aren't using these.
They are more than they were, but
1%.
But
so why is that though?
Many different reasons. Number one is that you don't capture the versatility. If you have less kind of options for your starting materials, you have less options for the plastics you're making out of them. So there is more development needed to create better versatility in what these materials can do and where they can be used. Because if you go to a company and you tell them, look, I've got this plastic, then it comes from plants, and they go, well, is it as good as my plastic I'm making currently that's really cheap and I can still sell, like, no one's stopping me from selling it? And you go, well, no, but it comes from plants. And they'll go, well, this is cheaper and better, so why wouldn't I? So there's a lot of room in the kind of jobs that we do in terms of making these plastics.
So they kind of can be used as applications, but quite often they're slightly pipped to the post still by oil.
A lot of the
in terms of their properties and their price.
When we talk to companies, one of the most common things we get is we've over-engineered the plastic we've got. We know we can get really high quality, really strong plastic really cheaply. So we don't know how much less of a quality of plastic we can get away with.
Right.
And so there's something on the part of companies to actually learn, well, we've over-engineered these plastics. We go for the toughest, hardest wearing plastics, when actually maybe they almost certainly could get away with bio-based plastics.
Right, because they just don't need... So it may be the toughest plastic in the world they've got.
Yes.
But frankly, for what they're doing, they don't need the toughest plastic in the world. It's a bit like a Formula One car. They make them as weak as they possibly can get away with, don't they? It's kind of... You could make Formula One cars much stronger, but they'd be really heavy and slow. So it's about scoping it according to your actual application.
We've almost been spoilt with how good the current materials are in that they'll not only outlast the use case we have for them, but they'll outlast us as well.
Okay, we've created plastics that are so good, they live forever.
Yeah.
And actually, that's probably not what we need them for. So yes, it's not as good at real plastic, oil-based plastic at living forever, but we don't want it to.
Yeah, I mean, the other big problem is that there's a lot of oil, we have a lot of infrastructure to do it cheap, and people would have to invest in the plants and the scale to make this more economic.
And are you getting a lot of people coming to you? Is it still kind of small?
We're getting loads of companies of many different sizes as well, anything from like a startup to a very large company trying to work with us on these issues, which is really encouraging to see. And there are a lot of, for instance, like PLA, I believe lots of like large scale plants are being developed, or at least one in Europe is, to make these on an even larger scale than they're currently being made. But that takes time, and that's why we're increasing the number of bio-based plastics we have and that we make, but it's not going to be instant, and it's not going to be overnight.
Right. And ICAST is based, of course, in Swindon.
Of course,
in Swindon, in Brunel's Railway Works.
Yes.
So just a few doors down from where I'm based, actually. But so it's good to see that's a kind of basically that kind of intercept between the research and all that kind of stuff and actually industry using it. So great to have it in Swindon. There was something you mentioned previously about neutron scattering experiments.
Oh, God,
Where does that come in? Because this feels like proper nerdy now. We've kind of done practical. Neutron scattering sounds a bit too nerdy for beating up plastic.
Yeah, this is something I was doing in my PhD. So it's not something an industry or company is suddenly going to start doing neutron scattering.
Okay.
But we were making a new type of plastic, and we were experimenting with how basically changing the shape of the plastic in terms of, as John said, a plastic typically is just you stick monomers together, and that's done generally in a chain. And I was playing around with how if you just made a ring instead of a chain, that noticeably changes the properties of the material that you're getting out.
Okay.
And the problem with that is it's very kind of poorly understood at the moment because it's very, very new. So we use techniques like neutron scattering to get an idea of the physical intricacies of these materials to better understand them and how they tick and how they could best be used. So it was more kind of work looking kind of 10, 15 years in the future. But once you make new materials which could help these be more versatile, you need to understand them before you can actually.
That's one of the fun things you use PhD students for, isn't it?
Yeah.
Here's this question, which we can't prioritise with real money yet and real staff.
Exactly.
But it might be interesting, it might be rubbish.
Exactly.
And a PhD student could be free to just, hammer the hell out of this particular one question.
Yeah.
What if we put it in rings? Might make no difference at all, might be rubbish.
Yeah.
But let's have a go and try. And so that's basically the kind of deep dive you did in your PhD.
Yeah.
Nice.
So we created a load of new plastics that hadn't been made before in that ring form, and we tested them against the typical kind of linear ones.
Right.
And we showed that there was some noticeable differences in the types of properties you can get out of them, and that might be helpful in terms of improving these versatility and helping us get more bio-based plastics into the world.
And that bit of work might sit in your PhD thesis on a shelf in the library forever and never be looked at again.
Probably
or
won't.
it might change, or it might just change the world and be the next super plastic that solves all our problems.
You never know.
But we don't know, which is why we do the research, I guess. Yeah. So what most excites you now about the future of this? What do you think which bit of research or bit of application or something do you actually get excited about?
Everything. I mean, in my eyes, the thing I get excited about is looking towards a future where all our plastic is bio-based and it's all being circular, and that we don't have to worry about, making global warming worse and polluting the environment with non-degradable plastic. That is the goal. And I think hopefully in the period of 20, 30 years, we'll get to a stage where bio-based plastics will become cheaper than oil. Oil is going to run out. It's going to get more expensive. This is the future. That's what excites me. Who knows what timescale that's going to be, but
would you put a timescale? Would you? We're talking 1,000 years,
no,
100 years, or 5 years?
I mean, how much oil is there left? I think they say somewhere between 100 and 200 years worth. So that would be the absolute longest period of time.
Right.
I think
it will be done in less than
yes,
that.
And if there was
more expensively.
Well, if there was such a thing as a carbon tax, we could do it now.
Right.
I think.
So it's about how quickly do we want to change,
exactly.
really? How quickly do we want to get rid of plastic?
Yeah.
Which is basically how quickly do you want to move away from oil?
Exactly. I think what's also been exciting is the reception that places like ICAST have received from industry and from all the engagement we've had from companies that are actively looking into these projects. So it's not just John and I screaming into the void saying use good plastics. It's companies willing to kind of work with us to make better plastics and to advance these forward.
I think they're screaming out for us academics to come along and basically say, look, we'll work with you. Let's do something together instead of X-ray scattering of cyclic polymers.
Yeah, exactly. No, exactly.
It's really coming together and solving problems that really need.
Yeah. And I tend to find that with companies, they do want to change mostly, but they are driven by commercial realities, and it's quite hard for them to do it without money from government or something to kind of move them on. So I guess you kind of provide a bit of that risk that they can't take commercially.
I should say our research is government funded. It's funded by Research England, so there is government money going towards these solutions that are effective.
So Innovate UK and those kind of bits. Yes. Yeah. Okay. So the future, you think we're going to be? You think realistically, these are going to work. We're going to be away from oil based and into plastic based.
I think there will be some kind of it will be an evolutionary kind of change. It won't just happen overnight, but we'll have at some point a mixture of much more plastics coming from natural sources, and we'll have much better kind of hopefully recycling methods and ways to deal with the current plastics that we have, and much more of a circular economy in many areas where plastics are used. It's not going to happen overnight, because it is tough to make materials and then also like get them to a point where they're exactly comparable in terms of the cost and the benefits and the properties with the industrial plastics. But you can definitely see a world in which we're combining these with a much more sustainable mindset towards plastics.
I do also think you probably won't notice. Like there's nothing intrinsically different when you look at that PLA versus other white plastics. And like, for instance, nearly all 3D printed material is PLA.
Right.
And yet when you look at a 3D printed plastic, you don't think this is made of plants.
No.
So,
you tend to worry about the wastage of plastic. Yeah,
exactly.
okay.
So actually, I think people probably won't even notice that the plastics are becoming bio-based as well.
Okay. So, I mean, yeah, when plastic first arrived, the very first plastics and Bakelite and all that stuff, it was kind of lauded as amazing wonder product, wonder material. It's going to solve the world. We quickly kind of started to fall out in love with it. But actually what you're saying, the future is plastic, but the future is green plastics. And it's kind of, it's actually coming, and we're going to get there. So John, thank you hugely for coming in, and thank you for the work you're doing at ICAST. It's kind of reassuring and actually, as you say, exciting. So we look forward to seeing more of this work, and we won't notice as a consumer. We don't have to change what we do, which is good. We're just going to start finding plastics are our friend again. So thank you very much.
Thank you.
Thank you.